we are delighted to have Shankar Narayanan to talk with us about achieving high performance with geo-distributed cloud applications. Shankar is a PhD candidate in the Department of Electrical and Computer Engineering at Purdue University, where he is working on his research with Professor Sanjay Rao. Broadly, his research interests are in the areas for computer networks, distributed systems, and cloud computing. His work primarily focuses on developing algorithms and building systems that improve the performance of geo-distributed, large-scale online applications. The work done by Shankar and group has won many accolades, including an award at the ACM Student Research Competition at SIGCOM, the flagship conference of the ACM held last year in Hong Kong. With that, I'm going to turn it over to Shankar. Shankar?
Thanks, Sridhar. Welcome to all, and a very good afternoon too. Today I'm going to talk about our work on achieving high performance with geo-replicated cloud applications. As we all know, modern web applications are becoming highly interactive in nature, which imposes stringent latency requirements on these applications. Typically, these applications have SLAs defined at the 90th percentile or higher of their response times. This also has serious financial implications. For example, Amazon finds out that every 100 millisecond increase in latency costs them 1% in sales. Google also finds out that a 0.5 second increase in delay causes a traffic drop by almost 20%. Also, these applications require a very high degree of availability, typically defined at the order of 5 nines or higher. This means that these applications necessarily need to be robust to failures of entire data centers. Unfortunately, we find that data center failures are more common than what we would expect or like. For example, the graph here shows the downtime per year that was observed in Google App Engine data centers. There are two key factors that I would like to point out. The first is that all these instances have a bunch of planned and unplanned outages. The second is the fact that these outages can actually last for a few hours. For example, the 2 episodes that are shown here in 2013 accounted to almost 4 hours of downtime. A common approach adopted by application developers to mitigate against such failures of data centers is to geo-replicate data and the application servers. This provides 2 advantages. It provides higher availability because there are now more application replicas that are available throughout the continent and the world. Further, it also lowers the latency because now applications and data can be placed closer to the users. In this talk, I'm going to present our work on achieving good performance from such geo-distributed applications. We'll focus on solutions at both the storage layer by optimally replicating the data in geo-distributed data stores, and also at the application layer by adapting these applications to variability in the cloud. I would like to first begin by talking about my work on performance-sensitive replication in geo-distributed cloud data stores. The focus here is on the performance benefits that can be obtained with optimal replica configurations. This was published at IEEE DSM this year, and the work is done along with my colleagues at Purdue University, Ashwin Sivakumar, and professors Sanjay Rao and Mohit Tawarmalani. As we saw earlier, application developers geo-replicate data across multiple data centers to mitigate performance failures. However, there are 2 key decisions that one needs to make when geo-replicating the data. The first question is, how many replicas do we need? And the second question is, where do we place these replicas? As one can imagine, both these decisions critically affect the performance and availability of the system. There are a bunch of other challenges with geo-replication. In particular, one needs to handle diversity and heterogeneity in workloads. These applications, yes.
Yeah, there's a question here. Shall I ask you the question right now, or would you prefer that you go further along?
Please do ask the question.
Okay. So the question is, what is the granularity at which the data is replicated? Are you going to be able to?
I will be talking about that in particular.
Okay. Thanks.
So, like I was saying, there's a bunch of challenges that one needs to deal when geo-replicating data. In particular, relevant to the question asked right now, we have to deal with the diversity and heterogeneity in workloads. For example, these applications have millions of data objects, and different objects do see different workloads. For example, in Twitter, a celebrity might see a very different workload from what a general user sees. Also, for these applications, reads and writes arrive from geographically distributed domains, which means that one needs to carefully balance both the read and write latency, both of which are critical. Further, these applications interactively share the data amongst its users, which means that it probably requires stronger consistency. A typical requirement for such interactive applications is that all users see the latest update. Note that this is very different from traditional CDNs and caches, where you primarily have read-heavy data, and the data comes from very few well-known publishers, but has significantly many more readers. Existing geo-distributed cloud data stores are designed along the lines of stronger consistency, like in the case of Spanner and Hypertext, or target lower latency, as in the case of COPS and Azure. These data stores also employ fixed replication policies like consistent hashing or chain replication, as in the case of Cassandra and Dynamo, which are prominent cloud data stores. Some of these data stores, like COPS and Azure, require full replication as well. This can turn prohibitively expensive for large-scale applications. Some data stores, like Spanner and Walter, do allow flexible replication, but these need to be manually configured. In contrast to all these cloud data stores, our focus is on the performance benefits that can be obtained with just optimal replication. Our primary contribution is a systematic framework for Replica configuration. We develop analytical models that can automatically configure replication policies for these geo-distributed data stores. In particular, we focus on two models: a model that optimizes the percentiles of latency and a model that optimizes the latency under failures. Using our models, we explore the fundamental limits on performance achievable with just replication. Our results are very promising. It shows that a reduction up to 3x to 10x latency is possible. We also highlight the importance of customizing replication decisions to the heterogeneity in workloads. For example, in our Twitter analysis, we found that we required as many as 2,000 distinct replication decisions in order to achieve optimal performance. Our primary contribution, one of our contribution is modeling.
Shankar?
Yes.
I have a question that perhaps maybe you're going to address this, but I guess would you have a definition for what you mean by optimal performance?
Yes, we would get why I call it optimal. So just to give you a brief preview of what is about to come, instead of going by heuristics and other solutions, we actually come up with optimization framework which uses analytical models, and we solve that as a mixed integer program. So essentially what that means is whatever solutions that our system generates are proven optimal solutions.
I see. And it's optimal with respect to performance and availability constraints.
Yes, I will be talking about the models in detail, so it will probably become clear at that point of time, I guess.
Okay, thank you.
Thank you. So like I was saying, the other contribution in our work is that we model various practical considerations, like for example, the asymmetric read and write latency thresholds that the application might require. We also model things like the relative priorities and writes, where one might want to prioritize the reads more than the writes. We also look at various cost-sensitive replication parameters like the bandwidth cost, the storage cost, and the compute costs. Finally, we evaluate our approach using real-world experiments on real-world cloud platforms using real-world application traces as well. Note that our framework is not a data store. It actually works in tandem with existing data stores and suggests optimal replication policies. Our initial focus is on quorum-based data stores, which is a prominent class of data stores. For example, Amazon's Dynamo and Cassandra are some prominent data stores. Quorum-based data stores borrow their ideas from classical quorum protocols, but tweak them for implementation reasons. We also target stronger per-object consistency, which means that any read to a particular object sees no version older than the last successful write. This is one of the common requirements for interactive applications because users interact among themselves and you need a thread of communication to happen in the same sequence across all users.
Is there a reason why you don't consider Amazon S3 as a data store?
So Amazon S3 is more like a blob service where you store a bunch of objects. They do allow replication across multiple regions, but they don't typically interface with applications directly. Moving on with understanding how quorum-based data stores work. Consider the following schematic figure where you have a bunch of data store and application server nodes deployed across the continent. Assume that the number of replicas that you want for each of your data objects is 3. Any read or write that is sent by the application server goes to any one of these data store nodes and gets forwarded to all the replicas where the data is located. And a success is returned if any 2 of them respond. The magic number 2 here is called the quorum size. In this particular example, it happens to be 2, but we shall look at how this can be a critical component in determining the replica configurations at a later point of time. Note that this configuration also happens to be tolerant to any single failure, as all we need is 2 replicas to respond for any successful read or a write. Moving on to the notion of consistency in quorum-based data stores, we would like to understand this more in detail because this is a critical component for all interactive applications. Remember that reads and writes are sent to all n replicas and a success is returned if a quorum number of replicas respond. Our aim here is to ensure that all future reads see a completed write. In quorum-based data stores, this condition would be true if the read and write quorums intersect, which means that R plus W should be greater than N. A simple example of this would be a majority quorum where the read and write quorum sizes are more than half the number of replicas. Intuitively, you can think of this as if there are more than half the number of replicas that respond for any read or a write, then it means that there is at least one intersecting replica that has the latest update that you might want to read. Of course, consistency in quorum-based data stores can be tweaked by tweaking these parameters. For example, if R plus W is less than or equal to N, then this consistency requirement is relaxed. As we can see, there are a bunch of configuration options that we need to decide when looking at replication in quorum-based data stores, and it is not trivial. We also find that naive strategies are often grossly inefficient, as we shall see. In order to understand this more, we looked at a real-world example from Twitter, which consists of a bunch of user timeline objects. The reads for those objects arrive from US West, and the writes for those objects arrive from both US East and Singapore respectively. We now consider 2 intuitive strategies that one might use for replication. The first strategy is to place the data at a location that is globally central to all accesses. In our particular example, this happens to be the US West location. Note that with this strategy, the maximum latency is going to be dominated by the link between Singapore and US West, which is 186 milliseconds. The other strategy that one might think of is a user-centric approach where we replicate the data near users. For example, in our case, it would be replicated at US West, US East, and Singapore because that's where the reads and writes come from. Note that with quorum-based replicas, we have now 3 replicas, which means that for strong consistency, we need a quorum size of 2. This implies that a maximum latency here would again be dominated by the link latency between Singapore and US West, which is 186 milliseconds. But can we do any better? Our framework, which adopts a systematic approach, places 4 replicas as shown in the figure with a read quorum size of 3 and a write quorum size of 2. This means that any read needs response from 3 replicas, but note that the maximum read latency here would be 117 milliseconds, which is the link latency between US West and Tokyo. Also, the write latency would be dominated by the link latency between Singapore and Tokyo, which happens to be just 95 milliseconds. As we saw from the example here, our systematic approach is able to exploit the asymmetry in read and write locations and intelligently increase the number of replicas and appropriately tweak the quorum size in order to actually provide lower latency. We now look at how we formulated these analytical models. Consider the following figure where you have a bunch of data center nodes where you have the application and the data store deployed. The primary input to our model is going to be the inter-data center latencies, Dij. We also require the fraction of accesses from each data center for these objects, which is Ri and Wi. We also accept as input some of the application constraints, like for example, the maximum allowed read or write latencies. It could be the read-write asymmetric priorities that you might want to assign, and a bunch of other constraints which we shall see later.
Shankar, there's a question here.
Yes.
Are data center latencies relatively static, or are they dynamic as well, and does your model accommodate that?
So our model right now models everything as a static value, but there is a strong reasoning behind why we choose this approach. Just to give a context or intuitive answer on why this would be true, think of a case where you have inter-data center latencies being variable. What we find from our extensive measurements on both EC2 and Azure is the fact that while these delays do vary a bit, they do not vary significantly enough in order to make a better configuration possible. So while there are changes, they don't really change that much. And it also comes from the fact that link latencies that are longer in nature show more deviation, which means that there is not a chance that you'll probably find a data center that is close by enough in lieu of the data center latency that goes back, which can make things work drastically better. So what we find is that a relatively static approach in terms of measuring these data center latencies at the granularity of, let's say, a day or maybe a week is sufficient enough for our models to actually work well in practice. Does that answer the question?
Well, I'll let the person ask the question for a follow-up or send me a chat, but for the time being, we can assume that.
Okay, thank you. So moving on, using these model inputs, we determine the number of replicas and we choose the correct quorum sizes R and W, and we also determine the appropriate location for these replicas. We cast replica configuration as an optimization problem, where the objective is to minimize the read and write latency subject to a bunch of constraints, like consistency constraints, including R plus W greater than N, which ensures that you have the read and write quorums intersect, like we saw earlier.
Shankar, there's another question.
Yes.
What is the logic for selecting the replicas for read and write? Are you going to be discussing that?
So the replicas are not independent for read and write, but the way quorum works is that you send requests to all the replicas, but you only wait for the certain number of replicas that respond, which means that the quorum size that a particular read or write meets is essentially what determines the latency of a particular read and a write. So in our models, we also look at optimization models which sort of optimize all the latency for all the requests, as well as for a certain percentile of the request that you want to meet up with.
Okay.
So moving on, we also have availability constraints, like for example n greater than or equal to 3, which means that you can tolerate up to any single failure. We also throw in a bunch of application constraints, like the 90th percentile of read latency being less than a certain number of milliseconds, or you want to prioritize reads versus writes for read-heavy applications. We cast this as a mixed integer program, as we shall see now. As we saw earlier, the objective here is to minimize the max of your read and write latencies, subject to a bunch of constraints. The variables QR and QW correspond to the quorum sizes. The indicator variable xj is 1 if the data center j hosts a replica. The indicator variable QRIJ is 1 if reads from data center I use the replica in data center j to meet their quorum. And Dij, as we saw earlier, is the latency between data centers I and j. We now look at some of these constraints one by one. The first constraint ensures that the read and write quorums intersect, or R plus W greater than N. The second constraint ensures that the data center j is added to the quorum for a particular request only if it has a replica at xj. The third constraint ensures that a replica j has to be within the acceptable latency thresholds. Finally, the last constraint ensures that there is sufficient number of replicas that meets the quorum for a particular object. While we only show in the talk the constraints for reads, symmetric constraints can be easily obtained for writes as well. We now look at the importance of optimizing various latency percentiles. To understand this more, consider the following example where you have 5% of the traffic arriving from the west coast and 95% of the traffic arriving from the east coast. Intuitively, This would mean that it is efficient for us to ignore the 5% that arrives from the West Coast and optimize the replication for the 95th percentile of the latencies. While this seems hard to model, we leverage on the following insights to extend our model. Recall that accesses from any given DC are likely to see similar latencies, because the latencies, even though they vary, they do not vary significantly to make a better, any other data center or any other replica being a better option for this. Using this intuition, all we need to do is to select data centers that add up to a required percentile. Using these insights, we extend our model to latency percentiles as follows. The new variables that we include here are the NRI, which is the number of reads from a particular data center. The indicator variable YRI is 1 if the data center, the reads from data center I is selected for meeting the required percentile, and PR corresponds to the read percentile that we want to optimize for. We add the following equation, which ensures that reads from data center I add up to the desired percentiles and not beyond that. The second equation, we extend the quorum constraint to ensure that we have sufficient number of replicas that exist in the read quorum. Note that this particular equation is non-linear. However, this can be linearized by introducing an upper bound to QR, more details of which can be found in our published paper. We now look at the importance of modeling performance under failures. Recall from our previous example that the maximum latency of access here was 117 milliseconds. Note that having more than 3 replicas ensures that the system is resilient to any single failure. This we call as our basic availability model. However, on the failure of a particular data center, for example, if the US West data center fails, the maximum latency shoots up drastically to 191 milliseconds. Recall that with more than 3 replicas, the system is still available. But can we do any better? We developed the N-1 contingency model to mitigate the impact of such failures. Our model was motivated by contingency techniques used in power transmission systems. The key insight here is to explicitly model the latency on a failure. Intuitively, this means that our models choose configuration assuming that any of the single failures could be possible. While we focus on single failures at the moment, this model can be easily extended to multiple failures as well. We adopt a 2-pronged evaluation strategy for evaluating our approach. One is using real-world experiments, and the other is by using large-scale trace-driven simulations as well. All our experiments are performed in a real cloud platform where we deployed a Cassandra cluster spanning across all the 8 regions and 21 availability zones of Amazon EC2. All our experiments are performed on the above 21 data center Cassandra cluster. The access patterns and geolocations for all our experiments were obtained from real traces of Twitter, which consists of 3 million objects from a 5-year-long trace, Wikipedia, which consists of 4 million articles from a 3-year-long trace, and Govala, which consists of 200,000 objects from a 2-year-long trace. We first try to answer the question, are our models accurate? In order to understand this, we compared our model predictions with the observed latency in our experiments. These experiments were performed on the 21 DC Cassandra cluster that we just described, and for a group of timeline objects from Twitter, and reads or writes were issued as per the trace. The graph here shows the CDF of the fraction of requests along the y-axis and the latency along the x-axis. From the figure, it is quite clear that the observed values are very close to the model predictions, modulo the fact that the observed reads include a constant 9 millisecond operational overhead of Cassandra that our system really doesn't capture. We now try to answer the question, how do we compare with existing schemes? In particular, we wanted to compare our schemes with the default Cassandra partitioner. This is again a large-scale real-world experiment on the 21 DC Cassandra cluster with more than 500,000 timeline objects from Twitter, and 6 million reads and writes were issued as per the trace. The graph here shows the CDF of the fraction of requests along the y-axis and the latency along the x-axis. From the figure, again, it is very evident that we are able to perform almost 3x better than the default Cassandra partitioner. This also clearly shows that a uniform policy is grossly inefficient. In order to highlight the importance or the need for workload-aware replication policies, we analyzed our observations a little further, and we found out that we required as many as 2,000 distinct configuration decisions in Twitter. We also found out that the benefits come not only from good location, but also from optimal replica configuration. To understand the impact of just the optimal replica configuration, we compared our scheme with a scheme that fixes the number of replicas to 3, but allows the best choice of location among those 3 replicas. Our results show that more than 15% of the objects in Twitter benefited from actually having more replicas. We also found that the latency reduction can be as much as 70 milliseconds in some cases. We now look at the benefits of optimizing latency under failures. Recall that the basic availability model, which ensures that there are more than 3 replicas, still is available under any single failure. Our N-1 contingency model, in contrast, explicitly optimizes for the latency under failure and is available under single failure as well. We performed this experiment for a 21 datacenter cluster on EC2 that we have been seeing so far, and for all English Wikipedia articles. The graph here shows the box plot of the performance obtained with both the basic availability and the N-1 contingency models. The y-axis shows the read latency in milliseconds, and the x-axis shows the time in minutes. We replayed various events, which includes the failure of certain data centers, and observed the performance of both the models under failures. As we can clearly see, the basic availability model, while still remaining available, performs drastically poor under the failure of certain data centers. Like, for example, when the US-based data center fails, the performance goes bad drastically. In contrast, our N-1 contingency model provides good performance under any single failure, which is 150 milliseconds lower than what the basic availability model provides. Surprisingly, we also find that we can provide good performance under normal conditions as well. This means that there is a big or a huge possibility that we can actually optimize for latency under failures without foregoing performance under normal scenarios as well. We now try to answer the question, how often do we need to reconfigure these replications? In order to understand this, we use configurations from a previous month's trace and perform and observe the performance for the current month. We do this for all the 3 applications, Twitter, Wikipedia, and Bovala.
Shankar, there's a question here.
Yes.
How, given the data, sort of the instrumented data that you get about, the inter-data center latency and the read-write frequencies, etc., how long does it take for you to run your model to actually come up with a sort of a configuration parameter setting recommendation?
Right. So actually, I have a slide on that, but let me just give you a brief, answer to that right away. From our experiments, we found that our basic availability model is able to solve within a worst-case scenario of 0.17 seconds, and our N-1 contingency model was able to solve within a worst-case scenario of 0.41 seconds.
So there could be some possibilities where this is sort of used in line and almost in real-time decision-making then.
So that's one of the things that we sort of try to look at in this particular slide, like how often do we do this? While there is a possibility for doing this in a more online fashion, what we find out is that the benefits are not as much. And moreover, if you think about it, these access patterns are not likely to be distinct for every individual object, but are likely to have some pattern for groups of objects. So one might not necessarily need to run this for every particular object, but can run it for a larger group of objects. Like, for example, all the objects that are belonging to a particular user, or it could be all, let's say, Wikipedia articles belonging to a certain language, right? So there are some patterns that sort of help you reduce the number of computations that you make. But modulo that, what we find out is that even an unoptimized version of our model that we implemented using Cplex is able to solve within half a second on a worst case scenario, which we thought is a very reasonable thing. It was something that that really surprised us as well. But even if the problem space sort of expands in the future, we have like a lot of techniques that we can use to cut down on the computation time. Like, for example, you can provide the Cplex solvers various cuts and things like that, or heuristics that it can actually use to prune these trees away when it configures this application.
So I guess just to follow up, but maybe you can defer this question. When you talk about doing this in worst case 0.41 seconds, etc., can you give us a scale? How many variables? How many servers? How many data centers? I think you said 21 data centers, right?
Yes.
So can you give us a scale of how big the model is?
So the model had close to, like, let's say 50 variables, and we thought this was probably a extended scenario, because right now you probably have 21 availability zones in EC2, which you can probably this is the worst case scenario that you will find in real world today. But we also tested it with an extended set of data center locations based on where Amazon Edge servers also locate, which happens to be like close to 31. And we found that the worst case scenario time doesn't really go much longer than 0.41 seconds.
Thank you.
So coming back to the question, how often do we reconfigure the application? What we find out for all the three applications is that using a previous month's configuration is sufficiently good enough for obtaining good performance for the current month. However, while we only show the graphs for the hourly or the monthly recomputations, we also did this extensive analysis where we looked at hourly, weekly, and daily granularities as well. And not surprisingly, we find that recomputing these things at an hourly rate does marginally better for 15% of all the objects in these applications. And we find that there is almost no difference between the others. However, we believe that recomputing it at an hourly basis doesn't probably make sense, because you get minimal benefits for just 15% of the objects, and for 85% of the objects you probably do not have any reason to do these recomputations. So from our observations, we find that a monthly reconfiguration sort of works reasonably well for most of these real-world applications. So a brief summary of some of the other results. We analyzed the performance of our approach with different latency percentiles, including 100, 90, and 75, and we find that the 100th percentile latency performs poorly, and the 90th percentile and 75th percentile performs pretty close to each other. We also tested the robustness of our configurations to delay variations in the cloud, which was one of the questions asked earlier. And what we find out is that our configurations are able to perform within 5 milliseconds for 80% of all optimal solutions that we could have come up with. We also, tested our approach with the feasibility for various asymmetric priorities between reads and writes, and it worked out pretty well too. Answering the question about time complexity analysis, we found that our basic availability model was able to solve within a worst case scenario of 0.17 seconds, and our n-1 contingency model was able to solve within 0.41 seconds. More details of all this can be read from the paper as well, so please do go back and check with it, and let me know if you have any questions on that as well. To briefly summarize some of the related work in replication and data placement, user-aware data placement has been studied in many works like SPAR and Wally, which sort of consider relationship between the data, but they do not, they model either eventual consistency or do not model replications, neither of which can be applied for interactive applications. Classical facility location problems minimize the cost of deployments, but carry no notion of consistency at all. For example, in facility location, having more replicas is guaranteed to reduce the access latency, which is not always the case in quorum systems. Classical quorum protocols have been well studied for decades along the lines of availability or reducing network delay, etc. In contrast, our framework targets quorum-based data stores and its practicalities. There are more recent works like SpanStore, which aims to minimize the cost by leveraging the differential provider pricing. And in contrast to this work, our framework is more generalized and includes many practical considerations like optimizing for latency percentiles, optimizing for failure scenarios, and other things. To conclude, we provided a systematic approach for replica configuration, and we showed that naive replication strategies are grossly inefficient. We also highlighted the importance of heterogeneous replication policies at a finer granularity and customized to workloads. We also showed the importance of modeling various practical considerations, including the application requirements and constraints like the latency percentiles, your read-write asymmetry, and other things. We also highlighted the importance or the benefits of optimizing explicitly for the performance under failures. And finally, we now present the Replica configuration tool that we built using our framework. This works out of the box for Cassandra and on EC2 based deployments, but it can be tuned to other environments quite easily. We made this tool available online, which is a web application, a few months ago, and so far it has seen more than 250 unique users from more than 25 countries, involving 500 plus sessions, with each session lasting for more than 6 minutes. The following slide shows a brief demo of how the tool works. As we saw earlier, the primary input to our system is going to be the fraction of reads and writes that arrive from different locations. The delays we have already measured from EC2 and use that as our input. For this example, let's assume that 100% of your reads come from US West and 80% of writes come from US East and 20% come from Singapore. We also let the user choose which regions you want to host replicas because of various policy constraints and stuff like that. And what our tool does is it configures 6 replicas with a read quorum size of 5 and a write quorum size of 2, with 3 replicas being in US West and 3 replicas being in Tokyo. Note that the expected read latency here is 117 milliseconds and the expected write latency is 95 milliseconds. These configurations are totally non-intuitive without a systematic approach. In order to understand some of these parameters that we can tweak, we add an additional input which says all reads now need to be satisfied within 50 milliseconds. Note that our system now configures 3 replicas with a read quorum size of 2 and a write quorum size of 2, with all replicas placed in US West. And now note that the expected read latency is 23 milliseconds, which is less than our threshold. In order to compensate for the lower read latency, the expected write latency now increases to around 219 milliseconds. As we can see, our systematic approach is able to give you performance guarantees not only under normal conditions as well as under failures as well. Before I move on to the next part of my talk, I would like to take any questions if there are.
There are quite a few questions, so I don't know. Well, let me go ahead and ask them, and feel free to defer the questions if you would like, Shankar. Okay. Mm-hmm. So, I guess the first question, the questioner asks: you talked about Cassandra partitioner and how your system does much better than that. Can you give a brief overview for those who are not familiar with Cassandra? What are the highlights of its partitioning mechanism?
So Cassandra, I actually talked about it in the slide, but Cassandra uses a hashing function, consistent hashing function, in order to spread data around equally across all nodes in the cluster. So essentially what it means that each node in your cluster is equally likely to receive a particular object that is being hashed to it.
Okay. Folks, those who ask the questions can please follow up with me either by chat or if you would like to ask the question via audio, please send me a ping as well. The second question is, where does this partitioning model break down? I mean, I guess I just noticed in the last demo that you did where you put in the constraint for the read latency and the system basically put all the replicas in US West, right? But that might sort of go against sort of an SLA requirement where the reason for geographic distribution is that you don't want any one data center to fail, right?
Right. So
is there
previous example, while we put 3 replicas, if you remember, each region in EC2 does have multiple availability zones which are supposed to guard against such failures. So in our example, we fed the 21 availability zones as existing data centers in our configurations, which is why I put all the 3 replicas.
I see. Okay. Okay, and I guess maybe this is for future work, but can this model be used for intra-data center optimization?
Absolutely. So if you think about it, this problem is just an abstracted placement problem in terms of how these inter-data center latencies or intra-data center latencies in this particular case would apply. So this model is not specific to anything, saying, okay, look, this has to be applied across data centers. If you are able to model your inter-data center or your intra-data center latencies, and if they are sufficiently diverse enough to warrant a model to be applied on top of it, this model is directly applicable to that as well.
So I guess a follow-up to that is, have you guys looked at that? Because I'd imagine that there's probably quite a bit of there are quite a few companies, quite a few apps that may not necessarily avail of multiple data centers, at the scale of Google or Amazon, but they may be, can certainly benefit from placement, policies, let's say within a corporate, within a large corporation, for example, within their data centers, right?
Right. So if you look at some of the examples that we've been talking about, we use an availability zone in a particular region as one of the data centers. And this can be extended to, further granularities, like you could probably say, okay, look, this rack within a particular data center, I want to treat it as a particular data center in my optimization model. And you can just run our optimization algorithm on top of it, and it will choose the appropriate strategies based on, how we configure the delays and how the request, read and write requests come from each of these different racks. So this model is directly applicable to any finer granularity, though we haven't really looked at it at this granularity because our primary goal was to target large-scale geo-distributed applications. But I don't see a reason why this cannot be directly applied to something at a smaller scale as well.
I guess there's one more question here. Is the choice of Replica independent of data size that needs to be replicated? For example, if I want to download a large file, I need minimum latency and have redundancy. Will this model apply? So
that's actually an excellent question. But I didn't really talk about the impact of data size in this talk, but our model formulations do consider how long it takes for a particular sized object. In other words, what I'm saying is, we also take into consideration all the bandwidth impact as well in determining, how these replications decisions need to be made.
So Shankar, just jumping in, I know you've got some other stuff to show, but there are a few more questions. Do you want to just hold on to those questions and finish the rest of your presentation, since we only have
I'll probably do that. I have 15 minutes, so I probably want to move on with the next part of the talk, which is also equally exciting. So I'm looking forward to all the questions, but I'll defer that to the end. Thank you.
Thanks. Go ahead.
So moving on to the second part of our work, which deals with application-aware request splitting for interactive cloud applications. Here, the focus is on performance benefits that can be obtained by adapting to variability in the cloud. This was published at ACM Connect in 2005, and the work is done along with my colleagues at Purdue University, Mohammad Hajat and Professor Sanjay Rao, along with David Moyes from Microsoft and Kunwadi Sipanit Kulchai from NECTEC Thailand. To give a brief review of how this architecture of real multi-tier application looks like, consider the following figure, where you have a bunch of logical tiers like the front end, the business logics, and the back ends. Note that there are multiple components in each of these tiers. Also, there are many instances of each component which could be potentially geographically distributed. These instances of components also have complex interactions between themselves and also with the users. In order to understand a little bit more about the scale of such multi-tier applications, we look at the following figure where we consider the components per application found in a Fortune 100 company. The y-axis shows the total number of components that we observed in the application, and the x-axis shows the various applications. There are two key observations that I would like to point out. The first is that all applications have many tens of components. Further, these components have multiple instances or replicas that are geo-distributed across multiple data centers. Note that in this particular work, we are talking about replicas in terms of application components and not just the data. In order to understand the performance variability in the cloud, we deployed and studied the performance of different classes of applications in the cloud. In particular, we looked at data-intensive application called thumbnails, which generates the thumbnails of pictures that the user uploads. This uses the blob as a backend storage. We also looked at communication-intensive applications like stock trader and day trader, which consists of many components and involves a lot of interaction between these components. We also looked at a social application called Cassandra, which is an open source application similar to Twitter. This is a large-scale application which uses Cassandra database as the backend. Like earlier, we perform our experiments on real cloud platforms, including Amazon EC2 and Windows Azure. While we did our analysis on all the 4 applications described earlier, in this talk I'm going to focus on thumbnail application deployed on Windows Azure for completeness. Recall that the thumbnail application involves the users uploading a particular image to the front end, which queues it up to the worker role for processing and stores the full version of the image into a blob, which is the backend. The worker role picks up this notification from the queue, and then processes the image by retrieving it from the blob and stores back the thumbnail into it. In order to understand the variability of performance in cloud when deploying this application, we deployed this application simultaneously in 2 different Azure data centers. And we monitored and measured the overall performance, the individual performance of individual components, as well as the inter-component communication performance. The graph here shows the box plot of the total per component and inter-component communication performance. The y-axis shows the delay in milliseconds, and the x-axis shows the various components and inter-component delays. What we find here is that there is high variability within component as well as between inter-component communication. From our analysis of these 4 applications, we derive the following key insights. We find that the performance across replicas of a particular component are often uncorrelated. We also find that only a subset of components show poor performance at any given time within a data center. For example, if the BL1 shows a poor performance in the example shown here, it might be the case that the rest of the components are actually doing okay. We also find that the performance problems are often short-lived. From our extensive analysis, we find that 90% of the problems last for less than 4 minutes. We look at some of the current approaches that are adopted today for handling variability. Auto-scaling is one of the things that really works well for workload spikes on any single compute component. However, note that not all components can be scaled in the cloud. For example, storage services like blobs are services which cannot be scaled by the consumer. Similarly, DB cannot be scaled by the consumer because these are services that are provided by the cloud provider. Further, events like network congestion cannot be mitigated by auto-scaling. Also, auto-scaling is typically slow to react, which takes order of few minutes in commercial clouds, and this is further exacerbated by the effects of things like cache warming, which might take for a while to reach optimal performance that your application needs. The other approach that is adopted for handling variability in cloud is DNS-based and server-based redirection. Note that in this example, if the link between front-end and business service goes bad, DNS-based redirection would redirect all user traffic to the front-end at the remote data center. However, with this approach, load balancing is hard, as one might overload components in the remote DC. Further, this is also expensive due to over-provisioning that is required at either data centers. This might also result in underutilization of resources because components that are actually okay in a particular data center are not utilized at all. Further, these DNS-based mechanisms are often slow to react and may take hours, as shown in some of the prior works. In contrast, our approach adopts a fine-grained redirection, where instead of redirecting requests when a component failure occurs entirely to a different data center, our approach routes the request around the problematic components and links. In other words, we use a combination of replicas across multiple data centers to serve requests. Note that our definition of data centers extends to geographically close by data centers, different availability zones within the data center, and also racks within data center. So this can be applied at different granularities as well. There are some design challenges with fine-grained redirection. One needs to be really careful when redirecting requests across data center. So our system goes remote only after it ensures that the delays of going across data center are acceptable. One also needs to be careful because there is a potential for us to overload remote components by moving traffic across to a remote data center. Therefore, we dynamically estimate the capacities of all components and links before making these redirection decisions. It is also important to minimize oscillations in routing decisions as well as handling stateful applications when doing fine-grained redirection. We present our system called Dealer, which is a system that helps component-level request splitting across multiple data centers for these applications. Dealer is a middleware that can be integrated with applications and adapts at a time scales of few seconds. Dealer can be integrated with many applications, and in our work, we integrated it with two multi-tier applications, which required only modest changes to the application code. Our results show that Dealer provides more than 3x reduction in tail latencies at the 90th percentile or higher when compared to DC level redirection under natural cloud dynamics. The following figure shows the system overview of dealer. While we do not delve into the details, I wish to highlight some key aspects of this design. Note that dealer resides outside the application and monitors the performance of components and links by obtaining performance logs from the application components, and it suggests routing decisions, which we call as the split ratios to the application. The following figure shows a schematic of how dealer works. As we saw earlier, dealer obtains the performance logs from the application and determines the latency of components and links that has been observed. Using this, it estimates the current capacity that is available in each of those components and links. Using these two information, it computes the appropriate split ratios, and ensuring that these decisions are stable suggests the split ratios to the application. We now look at how to estimate delays or components and links. In our approach, we instrumented these applications to measure the processing time at each component replica as well as the intercomponent delays. We leverage existing tracing functionalities like Xtrace or Dapper to achieve this. Our system also monitors the performance passively with the actual application traffic, and also in case of components that do not see too much traffic, we do active measurements using some test traffic. Using these, we calculate the split ratios, which can be done as follows. The input to our system is the delay matrix, which consists of the component processing and the intercomponent communication delays. We also require a transaction matrix, which says what is the workload that is seen at a particular link or a component. We also introduce the capacity matrix, which is the capacity of the component I in a data center M. Using all this information, our goal is to find the appropriate split ratios of transactions between any two components such that the overall delay observed by the user is minimized. Intuitively, the algorithm for calculating split ratios is a greedy algorithm which works in multiple rounds, where each round assigns requests to the best performing combination of replicas across multiple data centers subject to the capacity constraints. Note that our algorithm makes conservative decisions, does not over-assign requests, and this is possible because of the stability heuristics that we add. In order to ensure stability in the system, we smooth the delay values using weighted moving average across time windows with greater weight attributed to recent time windows. We also prevent abrupt shift across various combinations by applying damping and by gradually ramping up the traffic over time windows. These shifts also depend on performance seen in the previous windows. We also estimate the capacity dynamically by learning the threshold load beyond which the component delays might actually increase. We set these initial capacity thresholds based on conservative stress tests that we performed on each of these applications, and we adjust this threshold dynamically because the user or the mix of user requests may change over time in the system. We now answer the question, how do we integrate dealer with applications? As we mentioned earlier, our experience with two applications, including the thumbnails and stock trader, shows that we require minimal changes to the application. In particular, we just needed changes to the code at the connection logic between these components and also at the section of codes which handles state for these applications. Note that dealer only proposes split ratios and applications still make the final decisions whether to use these split ratios or not. We evaluate our system dealer using two applications, thumbnails and stock trader, which is deployed on two Azure data centers in US. Our workloads are real workload trace obtained from a campus web application as well as from Decabo benchmarks. We compare this with existing schemes, in particular DNS and server-based redirections.
Shankar, can I just jump in for 1 second? For folks that need to leave at 1 o'clock, please do fill out the survey, and so that we can tune our seminars so that they can be more useful to you. And for those that can stay on, Shankar has agreed to stay on for after 1 o'clock to answer questions. Thanks. Go ahead, Shankar.
Thanks, Sridhar. So, just circling back to, we try to answer the question in here as to how well does dealer perform under natural cloud dynamics. In order to understand this, we compare the performance of our application with and without dealer. The graph here shows the fraction of requests along the y-axis and the delay along the x-axis in log scale. As we can clearly see, dealer does almost 6x better at the 90th percentile or higher. But why did dealer do better? To understand this more, we did further analysis in terms of what happened when these various failures or performance degradations occurred. In particular, note that with dealer, as we see in the highlighted figure, dealer provides a significant improvement in delays under performance degradations when compared to the application without dealer. But why did it occur? We dug deeper into it and found out that in this particular instance, under a natural cloud scenario, we found that one of these business logics was observing a performance degradation, and dealer was able to redirect traffic to a remote DL in a different data center. But the graph here shows the fraction of traffic that was sent along each of those combinations of paths by dealer. And what we see here is that at the point when the degradation occurred, dealer was able to redirect successfully to components in the other data centers in order to ensure that we have consistently good performance. As we can see from the highlighted sections, during the performance degradation, the amount of traffic that is sent to a remote data center is at the same time being controlled is also optimally suited for ensuring good performance. We now compare dealer with server level redirection, which recall that server level redirection reroutes the entire request at the granularity of data centers by using HTTP 302 requests. We now compare the performance of dealer and redirection under the poor performance of a particular component. Note that this is based on a real issue that we observed in Azure SQL, where a subset of users in a data center observed poor performance. We evaluate dealer and server level redirection under this scenario. The graph here shows the total response time along the y-axis and the time along the x-axis. And what we find here is that dealer does significantly better when these performance outages occur. To understand more what happened here, we look at the fraction of traffic that is sent along the same data center as well as what was redirected to remote data center. From the figure, we see that during the performance impact, dealer was redirecting traffic to the business service in the remote data center. In contrast, note that DC level redirection can only a smaller fraction redirect only a smaller fraction because of capacity constraints that exist at the remote data center. This clearly shows the benefits of redirecting requests at component granularities. We now compare the performance of dealer with redirection when there is a transient overload in a particular component. The graph here shows the total response time along the y-axis and the time along the x-axis. Note that dealer does significantly better when a particular component gets overloaded. To understand more, we looked at what exactly happened under the scenario. We find that a particular business logic component was performing poorly at a given point of time, which is around 500 seconds in our example. And server level redirection redirects the entire traffic to a remote data center. This in turn affected the business logic 2, a component which was there in the remote data center due to traffic overload, and resulting in very poor performance as we see from the spike in the graph above. In contrast, dealer carefully redirects based on the capacity and ensures that the traffic that pertains to BL1 is redirected to the remote data center. This ensures that you not only optimize for the right amount of traffic that you need to send, but also take into consideration how much traffic the remote data center can actually handle. And as we see from the graph above, the benefits of dealer is quite significant. To conclude, we presented dealer, which is a system that handles cloud variability in multi-tier interactive applications. We also highlighted the importance of routing at component granularity, in particular dynamically routing requests across components replicas in multiple data centers. We also showed the benefits of adaptation at shorter time scales in the order of tens of seconds. We also showed the performance benefits of our approach, which performs 6x better under natural cloud dynamics and 3x when compared to coarse-grained redirection like DNS-based global traffic manager. With that, I would like to thank Purdue University, NSF, NetApp, and Google, without whom this project would not have been possible. I would also like to thank Sridhar and Milibo for providing me this platform and opportunity to talk to you all and present my research. With that, I would be happy to take any further questions. Thank you.
Folks, thanks, Shankar. Folks, for those of you that need to ask questions, please send them to me via chat or else, indicate as such, and I'll unmute you to ask the question. So I guess while we wait for people to ask questions, I guess one question that has come in is, administrative traffic, that is, inter-data center traffic, that involves backups, for example, that companies need to do for administrative purposes, or log analysis, for example, transmission of log files. Those kinds of data workloads are fundamentally different than, say, user workloads. Have you factored that into your data center optimization algorithms?
So if you look at what happens when you have large files being shunted within a data center, typically what happens is you reach a bottleneck constraint in the network, right? So any traffic that goes through that particular link in the network will see a performance degradation. And in our approach, we instrumented the application to monitor not only just the components, but also the various links between the components. So any such activity that is going on in the network would actually result in performance degradation of that particular link, and that would get reflected in the performance logs that we monitor from the application. So yes, these things are accounted for when we monitor these applications and make those decisions appropriately.
Because if I recall right, a couple of years ago, the Google App Engine downtime that you talked about was actually occurring as a result of interference of normal user traffic with, I guess, some administrative traffic that some process basically ran amok, right? I don't know if you can shed light on that, but it would seem to me that the two kinds of traffic can sort of tread on each other.
That's absolutely true, and there's a lot of instances that we have observed as well where things like backups really trouble the network. But then neither of our algorithms really need to differentiate between what constitutes a normal user traffic versus what constitutes an administrative traffic, right? So all we're looking at is what link or what component performs poorly at a given point of time, and we try to route requests around that problem. So it doesn't really necessarily, we need to look at what class of problem that is occurring in the data center to actually make these decisions. So in some sense, what I'm trying to say is our approaches are independent of what kind of problems. All we need to know is there is some problem that is occurring and which we are able to monitor successfully.
Okay, thanks. There's a question here that's come about dealer. I guess, can you shed some light on what, when you talk about application, the questioner is assuming you're talking about things like web servers and sort of prominent app servers. Is that fair?
Yes. So at least in our notion, most of these applications that are deployed in the cloud are typically application servers or web servers which have a RESTful API and uses standard HTTP protocol. So in some sense, yes, you are right that we are targeting these classes of applications.
And can you shed some light on you talked a little bit about log analysis of those apps, as well as potentially making some changes into those apps so that you could instrument into them to make the sort of the recommendations in dealer. Can you shed some light about the kinds of changes you had to make?
So the kind of changes that we've made were fairly simple. So if you think about what we really need is to know how long it took for a particular request along its path at each component and across each links. So all we need to do is to instrument the endpoints or where the logic where the applications connect to a different component. So all we needed to do there was to insert our instrumentation code at those points. And I think most of these applications that have been deployed, there are a bunch of nice instrumentation tools that are easily integratable with these applications. Like for example, X-Trace and Dapper are like wonderful tools that have been used in production for a while now. So these things are the ones that we sort of integrate with these applications at the point where the applications talk with the components in the application talk with each other. So those were the minimal changes that we really required to make. We didn't really make changes to the application code as such. The entire system is independent of what the application logic does.
Thanks. A questioner asks, you've talked about all the things in your model and how optimal it is. Sort of being a devil's advocate, what are the things that you're not telling about where your model breaks down?
So Okay, so I think we are referring to the work on performance-sensitive replication in data stores.
Well, I guess more broadly, I mean, this is just a question. I don't know if there's any particular detail around it, but the question, maybe you can address it as broadly as or as appropriately as you think.
So, in terms of something that really intrigued us when we were actually working on this problem was this intrinsic variability in the cloud, and how that would affect these data placements, and what happens if you really needed to shift these data across in a very crazy fashion. It requires a lot of cost, bandwidth, and other things. So one of the things that we really extensively looked at, which we didn't model in the end because of our decisions that I told you about earlier, is the how to handle these intrinsic network variability. In some sense, if you look at it, the N-1 contingency model actually tolerates some of these variabilities in the cloud that you'll find. And also we found that we did some stochastic estimates on how these delays panned out, and we found that links with larger latency typically have more variation stochastically and dominate the smaller links. So which means that you couldn't have really done too much better if you were to model all these minor link variations and extend our model from being MIP to more stochastic model. So we didn't really find too much benefits in that. So I think that was one of the things that we didn't really model. So that and the only reason why I could think it would break is you have suddenly a lot of data centers that come up very close to each other in a way that it breaks this stochastic dominance. So that's probably the only case where I would think our models might probably work suboptimal, which I don't really think it happens, because there's no point, like coming up with data centers that are very close to each other in terms of where it is. And likely, even if they were to come, the performance benefits by moving to a different data center is not likely to be as high.
Okay, folks, any other questions? I guess while we're waiting for that, I guess let's, there's going to be a webinar, follow-on webinar on August 22nd, when Dr. Gautam Atluri, from the postdoctoral researcher at University of Minnesota, will present a webinar on mining neuroimaging data to explore brain dynamics. So I guess if there are no further questions, Shankar, thank you so much for a very informative presentation. The slides will actually be online shortly, along with the YouTube recording that feel free to forward it and watch it, etc. You can also send questions to Shankar either through me or through his coordinates, which will be on the slides. And hopefully this was useful. Please do fill out the seminar surveys with your comments and suggestions for both topics, speakers, as well as ways we can improve them. And continuing past tradition, and there are quite a few people who have joined us for the first time, please unmute your microphones right now. Obviously, these seminars being done virtually, the speaker is in Indiana currently, and let's all give him a warm round of applause. So thank you for an outstanding presentation. Thank you. So I guess with that, Shankar, it's a wrap. See you all on August 22nd. Thank you so much.